take another problem. This is the rod of mass m and length L. It is hanging by a light ring, and the ring is moving along a smooth horizontal bar, and this bar is rigid. If the ring accelerates, moves with a constant acceleration a0, the rod will get inclined. The rod makes an angle theta with respect to vertical. We discuss the types of equilibrium the rod possesses. The rod will possess how many types of equilibrium, and find the accelerations, both linear of the center of mass and angular, and find the angle theta. If you draw the FBD, the rod will push this rod or this bar will push the rod or the ring up with a force that is called reaction force Ny. There is no reaction along this direction because the bar is smooth. Therefore, we just write N, normal reaction. Gravity is there, acting at the center of mass of the rod. Under the action of these two forces, the rod is moving. Condition is that the rod makes an angle theta, a constant angle theta, when this point or this ring moves with a constant acceleration. We have to calculate all these things, and we have to discuss the nature of equilibrium the rod is possessing. So, we have two equations. One, force equation, and second, torque equation. Now, we have to check whether the rod is in equilibrium or not. It is given that theta is constant. The angle of inclination of the rod with respect to this fixed axis is a constant quantity. Therefore, we have to start from this. Therefore, d theta by dt is equal to 0, and d theta by dt is nothing but angular velocity is equal to 0, and therefore alpha is equal to d omega upon dt will be equal to 0. This concludes that the rod possesses rotational equilibrium. The rod is in rotational equilibrium. Now let us calculate the acceleration of the center of mass. If the acceleration of the center of mass will be non-zero, the rod will have a non-equilibrium case. For translation, if the center of mass acceleration will be zero, the rod will possess translational equilibrium. So for this we need to calculate the acceleration of the center of mass. The acceleration of the center of mass of the rod is equal to acceleration of the center of mass with respect to the ring point P plus acceleration of this point P. Now we need to calculate acceleration of the center of mass with respect to the ring, where the acceleration of the ring is given as n naught I cap. It is given, and this is interesting. That's an interesting matter, even though it is very simple, but you have to calculate it. But our common sense will show that, our common sense tells us that since the rod is not rotating, it is a clear-cut case of translation. Since the rod is not rotating, its or the acceleration or velocity of all points of the rod are equal. So the rod is under pure translation. What does it mean? This point moves with velocity v, 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 this point moves. All these points will move with same velocity, and all the points will move with same acceleration. The velocity is dotted line. This point moves with same acceleration, and that is what we call acceleration of the rod, that is n naught, or center of mass also will move with that acceleration. ACP will be equal to 0, I will tell you. Since AP is 0 and AP is A naught I cap and ACP is 0, AC can be written as A naught I cap. Not only the center of mass, for this particular problem, all points will move with same acceleration, that is A naught I cap. Hence, the rod is in translational, is in or is not translational equilibrium. The rod has rotational equilibrium, but it doesn't have translational equilibrium because AC is not equal to 0. Discuss the types of equilibrium the rod possesses. The rod possesses only rotational equilibrium. The first part of this question has been answered. Let us come to the second part. Accelerations. AC is equal to how much? AC is equal to A naught I cap, answered. What is alpha? Alpha is equal to d omega by dt. But what is omega? 0. So alpha is 0. Already we have answered it. Then we have to find theta. To find theta, we can write force equation and torque equation. Let us write the force equation. What are the forces acting? Mj and N. N up, Mj down. This is the net force acting y direction, is equal to M into ACY. The center of mass moves with a constant acceleration along horizontal direction. Therefore, its vertical component is 0. So, Ay is 0. Therefore, N is equal to mg. Answer. So, find theta and N. Calculated. Fourth equation gives us the normal reaction. And we will see what torque equation will give us. We can write the torque equation. Torque about which point? That's interesting. Torque about, when you are writing torque equation, torque about which point? Let us discuss the torque equation now. We have to write the torque equation now. If you draw the forces, gravity, normal reaction, and this point accelerates with constant acceleration. We know nothing at present except these two forces. With these two forces, we have written the force equation. Fy is equal to mcy. Since the center of mass moves in a straight line with same acceleration a naught, its component along y direction is 0. Therefore, net force along y direction is 0. And net force is equal to N minus mg, that is equal to 0. In this way, we can get N is equal to mg. The normal reaction will be equal to weight of the rod. Now, torque equation. How to write torque equation? About, suppose, center of mass. About the ring, we have taken at the ring, we have taken the point P as the point P as the reference. You take P as the reference, tau phi is equal to Ip into alpha. You take the center of mass as the reference, tau c is equal to Ic into alpha, because you know alpha is same, and here alpha is equal to 0, we have proved, where alpha is equal to 0. This means that tau phi is equal to 0 and tau c is equal to 0. If this is the case, about this point, if you take the torque, this point is the ring, but the ring, you are standing on this point or standing on the ring, this is the reference frame now, and this reference point is accelerating, it is an accelerating reference frame. Therefore, you have to impose a pseudo force in opposite direction at the center of mass. Magnitude is m0, a0 is the acceleration of the reference frame, and direction is opposite to a0. Okay. So, we have two forces. You take the ring as the reference frame, pseudo force, gravity force, normal reaction force. Since the normal reaction force passes through this point, cannot produce a torque, and these two forces will produce a torque about it. Let this angle be theta. This force, pseudo force, will produce a torque that is equal to m a0 into y. In which direction? It tends to rotate the rod in this way, clockwise direction. Gravity tends to rotate the rod in anticlockwise direction. So torque due to gravity plus torque due to pseudo force, and torque due to normal reaction will be 0, will be equal to 0. The pseudo force torque will be m a naught into this distance, y in which direction, minus k cap. Gravitational torque produces the gravitational force produces the counterclockwise torque, that's equal to mg into x. Mg into x, this is the line of action of gravity, this is the perpendicular distance x. For pseudo force, this is the line of action, and from this point this is the perpendicular distance y. Basic concept of torque, mg into x plus k cap direction, anticlockwise direction, x upon y is equal to a naught upon g. But x upon y is equal to tan theta. So you can write tan theta is equal to a upon j, and theta is equal to tan inverse a upon j. So we have calculated that theta, angle of inclination of the rod, is equal to tan inverse a upon g by using the concept of torque about the ring, the accelerating point. You should get same answer by applying the torque about center of mass. But center of mass frame, the torque equation tau c is equal to ic into alpha. Alpha is 0 because for both the cases alpha does not depend upon the reference point. When alpha becomes 0, tau c will be equal to 0. So what is tau c? Let us calculate. The center of mass frame, let us write the torque. Tau c is equal to 0. Well, when you are standing on the center of mass, now you shift yourself from the point P to point C. This is center of mass, this is the reference frame. This moves with an acceleration a naught. There was pseudo force m into a naught in opposite direction of a naught is acting at the center of mass. Since the pseudo force passes through the center of mass, it cannot produce a torque about center of mass. Since the gravity passes through the center of mass, it also cannot produce a torque about the center of mass axis. Always you have to mention or remember that the axis is z axis passing through the center of mass. So this torque has components due to pseudo force, due to normal reaction, due to gravity is equal to 0. Gravity and pseudo force will pass through the center of mass, therefore the torque will be 0. That matter we have discussed in the concept of torque. The torque is produced by the normal reaction. The normal reaction torque is equal to 0. But torque produced by the normal reaction is equal to normal reaction, this is the line of action. This is the line of action of the normal reaction, and this is the point of reference. The perpendicular distance is equal to x. So normal reaction into x, in which sense this will rotate the rod, or it will tend to rotate the rod, or turn the rod in counterclockwise direction. Kf is equal to 0. Since n is equal to mg is not equal to 0 and x is equal to, this is L by 2. L by 2 sin theta is not equal to 0, n into x cannot be equal to 0. This is an apparent contradiction. So, this is a contradiction, but this contradiction is apparent. It seems as if it is a contradiction. So, how to sort out this matter? Normal reaction will produce a non-zero torque, but our theory says that net torque is 0. These two forces will never produce a torque because they pass through the center of mass. Therefore, normal reaction torque will be 0, which is not possible. Therefore, we have to assume another force. We have to predict, or we have to understand the presence of another force whose torque will be exactly equal and opposite to the torque produced by the normal reaction force about the center. From where that force is coming, let us see. That can be cleared when you write the force equation along x direction. Y direction force equation is over. Along x direction, that force along x direction is equal to mass times the acceleration of the center of mass along x direction. Since the center of mass is accelerating along x direction only with an acceleration a0, the net force acting on the rod along x direction is not equal to 0. So, there must be a horizontal force acting on the rod. There must be a horizontal force acting on the rod. What we have not shown in the free body diagram, we have to show it. Now, question arises, where does that force act? You may assume that force may act at the center of mass. When you take the force at the center of mass, again you are getting 0 force, 0 torque, and will be left behind with same contradiction. So, you have to assume that somebody is pulling this ring towards right by applying a force from outside. So, this is the external force Fx we can write. When you take the torque, now we have two forces acting at this point, normal reaction force and the external force, or the force applied by the external agent who is pulling the rod, catching this point ring. If you catch the ring and pull it, you are pushing or pulling the ring in this direction. So, you have to apply force here, and this force will produce a 0 torque about it, and it is quite understandable. So, the net torque will be 0 only when you add another force. If you consider the presence of the another force which is given by the external agent, the pulling agent, that is none other than the external force acting in horizontal direction will be equal to 0. If you add this torque, then you will get the correct answer. These two will produce 0 torque. So, torque produced by the external agent will be equal and opposite to the torque produced by the normal reaction force. External agent is applying the force Fx. This produces a torque. This tends to turn the rod about the center of mass axis in clockwise sense. Therefore, this will be minus nx. This is a line of action Fx. This is a line of action of Fx, and this is the perpendicular distance for this. This is equal to y. So, Fx into y. In which direction? Minus k cap direction or clockwise. So, with respect to this center of mass, these two forces will pass through the center of mass, cannot produce a torque. Therefore, these two forces will definitely produce non-zero torque individually about the center of mass. If you add these two torques, you must get 0. The torque produced by normal reaction is equal to n into x. Which direction? The normal reaction will tend to rotate the rod in anticlockwise sense or positive kickup direction, and the horizontal force will tend to, this force is tending to rotate the rod in clockwise direction with a torque which is equal to fx into y, and the summation must be 0. It is quite feasible and understandable, and physically it is possible. What is fx? Already you have calculated, m into a naught minus plus, what is n? N is equal to mg, we calculated, and is multiplied with y, it is multiplied with x is equal to 0. So x by y is equal to n naught by g, and x by y is equal to how much? Tan theta. Therefore tan theta will be equal to a by j. Exactly same answer we are getting by using this concept idea. So in this reference frame or reference point, the center of mass point, if you don't include this force by mistake, you will be getting erroneous answer, absurd answer or contradictory answer. But this contradiction will be apparent, can be avoided when you can understand that this force is present, this another force is applied at the ring to accelerate the rod, so that the theta will be constant for all these points of the rod. They will move with same acceleration. The rod will have 0 angular acceleration, and all the points will have same linear acceleration. The rod will therefore will possess or exhibit pure translation, no rotation. Let me clarify the doubt of that relative angular acceleration of this point P with respect to C. That will be equal to, let me clarify one point here. This point, all the points of the rod will move with same acceleration for this case. So if you take a point here, let's P, let's see, A P C is equal to, you stand here, you can see that there is no relative acceleration along this direction, is equal to 0, because alpha is 0. Since APC is equal to L by 2 into alpha, and alpha is equal to 0, AP will be equal to 0. In this way also you can prove. This gives us the idea that AP minus AC will be equal to 0, or AC is equal to AP is equal to AQ is equal to AN. So all the points of the rod will move with same acceleration. In this way also we can understand by using the concept of relative acceleration. The point, any point of the rod will have same acceleration. So the rod is in rotational equilibrium, but not translational equilibrium, because acceleration of the center of mass is not equal to 0. That's the idea.